At the beginning of the session, so thank you for being there. We were asked first to start with the end of the previous opening session. Just to remind the announcement, you have still some slots both for lightning talk and for bird of feather. So you can register. You have here the online site where you can register. It's not easy to find it on the BiDS website, so please write down this exact address so you can register for the slots which are still available, and you have all the information on the conference website for the program and so on. So we will begin the first technical session of using artificial intelligence for monitoring and predicting. It's basically focused on Earth observation, and we will move to other topics such as universe science in other sessions, but here we will speak about Earth monitoring and the following of what Philippe Sier has shown us before. The first talk will be given by Stefan Ralsel. It's about a versatile AI-based framework for high-resolution land monitoring at a global scale. So please, Stefan, if you can come, we will start because it's just the time. So each talk is about 10 minutes, and we will have 5 minutes for question and answers each time. So,
yeah. Thanks for the introduction. So hello, everyone. I'm Stefan Ralsel. I'm working for GeoWill at Innsbruck, and I'm here to give you an overview on the processes that we are using in the company to process large amounts of data, to transform these amounts of data to a set of output variables. So with variables, I mean, for example, land cover map, but not exclusively, a source of information that can be used by decision makers, for example, that can be used as an independent data source that's extracted from remote sensing data. So from a technical point of view, we are basically extracting the information from three main sources. The first source is the spectral domain, so to say. So you could call it the color of a certain pixel. The second one is the temporal domain. So how does a certain pixel behave in time? So we are using a full time series of data. And the third one, also very important, is the spatial domain. So basically, how does the neighborhood of a pixel looks like? So how is the structure in the neighborhood of the pixel? For that, we are using, of course, an AI-based approach. Yeah, so as a main data source, we are using Sentinel-2 data, so optical data, but that's also not exclusive to the workflow that we have. We can also, and we did incorporate Sentinel-1 data, and that
is starting in whole lab.
Yeah. Thanks. So yeah, we are not bound to a certain data source. It's just that we are mostly using Sentinel-2 data for our predictions. The operational context we are acting is the big data context, obviously. We require cost-effective and fast processes, robust processes that can be executed on a large scale. So the methodology we are following basically consists of two main building blocks. The first one is the pre-processing block. So this is basically the part of the workflow where we transform the large set of input data, so the big data part, to kind of smart representation of the data, and for that we found it very useful to follow an ordinary least squares approach that's depicted here, where we fit harmonic curves to the input data. So this basically covers then the temporal part of the input data that I mentioned before. And this ordinary least squares approach, that's very convenient because, first of all, it's computationally very effective. So it's computationally kind of comparable to the calculation of a mean value. And you end up with a fixed set of output coefficients. So, and these coefficients can model the full time series of a certain pixel. Yeah, so we start with a variable set of input layers, so to say. So, for example, band 2 of Sentinel-2 time series. We feed it into the process and we end up with a fixed defined set of coefficients, fixed set of layers that then can be used to do the predictions. And we are doing this on, yeah, not only on one band, of course, but depending on the application, of course, on a multitude of bands, which then covers the spectral part of the information extraction, so to say. So that's the first part, and in the second part, that's the prediction part. So we have now a defined set of parameters that can be fed into a machine learning model. For this part, our go-to method is the UNet model. And yeah, this UNet model as a convolutional neural network can cover the spatial part of the information extraction process. Now, the computationally most demanding part of the process is the training of the model. And basically what we want to have is a situation where we have specialized models, so a specialized set of model coefficients on each part where we want to carry out our predictions. We are mostly acting on a Sentinel-2 tile basis. It's also not restricted to this grid, but that's the most convenient way. And if we would train our models from scratch for each tile, that would take a very long time. So here we are following a transfer learning approach where we start with a generalized model that's trained on a larger scale. So for example, on a UTM zone. So we built a generalized set of model coefficients from scratch. That takes about 3 hours on a usual machine with a GPU. And this generalized model is then transferred to a specific tile where it's fine-tuned. The fine-tuning process from the generalized base model, it's quite fast. It's maybe half an hour, something in that order of magnitude. And from there, once we have the first model that's fine-tuned for a specific tile, we'll basically hop around in the neighborhood and only continue by fine-tuning specific models. We end up then in a situation where we have specific models for each Sentinel-2 tile. And this then goes into the IT part of the workflow, you could call it, where it's distributed to a configurable amount of workers, a configurable amount of virtual machines. And this is done by containerizing the workflow into Docker containers that can act independently and that can be deployed to a multitude of workers. This is done by Nomad as an orchestrator. So this brings me to some examples. I'll just show you the examples. Maybe we can cover some details in the questions then. I have 3 examples. The first one is large-scale production. This was done for the HRL non-vegetated land cover component. Specifically, it's an intermediate product where we predicted the built-up densities, so the built-up fraction per pixel on a European scale. And what you see in the zoom is Vienna, and in the upper part, a close-up of the place where we are right now. The second example that I want to show is a land cover classification with a quite detailed set of classes. But that can also be done in the same workflow. This was used for as a support layer for greenhouse gas reporting. And the third and last example was above ground biomass estimation that we carried out in Mozambique, in a certain province of Mozambique. And what you can see here, we also did a comparison to a pixel-based model, so that's an RF, random forest-based model with, where we had a root mean square error of around 30 tons per hectare, and we could lower this error to around 30 tons by hectare by exchanging basically the AI part with the unit approach. So yeah, I hope I could give you an overview on the approaches that we are using at GeoWill. What's next? The first example that I showed you will be carried out on a global scale. We will produce the global human settlement layer. So it will be a very similar approach, very exciting, because this will be the first time that we actually execute it on a global scale. And of course, we will constantly improving the algorithms behind in both the pre-processing part and also the AI part of the workflow. So, thanks for your attention.
Okay, thank you very much, Stefan. We have 5 minutes for question and answer, so please ask all the questions you want.
Thank you for the presentation. I have one question on the transfer learning. I'm here.
Yes.
Okay. About the transfer learning method, how do you fine-tune? Do you retrain the model with new data where you have it? For example, if you don't have good quality data if you work at the global scale, do you use some other layers or ground truth data, because it's usually not available in Africa, for example?
Yeah, so basically so if the input data is not enough, so to say, to have a good prediction, we can also use a model that's trained on a larger neighborhood of a specific tile. That's also possible. But basically, so what we are trying to do is to always build a model for a specific tile. We are lately also collaborating with a company that is producing artificial training data in a generative AI approach. So that's also possible to basically produce, in this case, for example, in the case of built-up prediction, to produce artificial built-up layers together with training masks. So that's in development. In the end, there are multiple options you can follow. Of course, if the input data is not enough, and if also the surroundings are not enough, then you have to find some other means of coming to a model that is able to predict it in the most accurate way possible.
Okay, thank you.
We have time for one last question, so on the left, thank you.
Okay, and if you train a model per tile, how you manage the stitching of the tiles then? Do you have some inconsistencies between the tiles?
It's mostly quite clean, I have to say. That depends also on the input data, of course. But it's mostly clean, and we are also doing, so we are predicting a larger spatial area, and then combining the produced tiles with a smooth merging approach, so with some gradient at the edges.
Thank you very much.
Thank you.
We'll continue with the next presentation on early warning for alpine drought.
All right. Hello. Good morning, everyone. I'm Mohammad Usman Liaquat from Institute of Earth Observation, DROUGHT Research, Italy. And today I am going to present the development of drought early warning system, which is one of the use case of the Intertrain project funded by the EU Horizon. So these are the outlines of my presentation, starting from the problem statements, overall research objectives, then the type of the data availability, workflow description, type of surrogate model experiments, initial results, and future outlook. As we all know that ALPS have been considered as the water tower of the Europe, containing glacier-rich mountains, snowpack fields, and underground aquifers. However, in last couple of years, ALPS has faced several drought events. Traditionally, process-based hydrological models have been used to examine the terrestrial water cycles and extreme events like floods and droughts. However, it demands an extensive amount of data and lengthy calibration, which is sometimes quite difficult to obtain, especially in a data-scarce regions or in catchments. In overcome to these issues, nowadays, as we have an idea about the machine learning applications that provide us some substitute solutions in order to tackle these issues. However, still machine learning applications have their some gaps. For example, okay, if they demand also the data, but sometimes they are not considering the physical aspects of the hydrology or hydrological cycles. In order to bridge these issues, so there is a one famous quotation from the Professor Shen that maybe the one day the deep learning model will be also like the important components also in hydrological modeling field. So in order to fulfill these gaps, we have now planned our case study into the three main objectives. The first objective is to set up the physical base model, and then developing its surrogate model by using the machine learning applications. And the second objective is to calibrate the parameters of the hydrological model and then implement into the deep learning model. And once we have trained our model, we will use the seasonal forecast data to predict and identify the drought affected areas. So this is the case study that we have using in our project. So we are using over the whole alpine region. In order to keep the hydrological variability, we have divided over the whole alpine region into the 21 catchments. So you can see here like the Piave, Adige, the Danube, and all the one. And then these are some of the main characteristics of all the catchments. And we, as a case study, as a starting, we have used the Adige catchment as a starting case study. As I have mentioned, we are as a first step is to use the physical base model. So as one of our project partners, we are using the WFlow model. It's a hydrological model. And we are using WFlow SBM configuration to compute the hydrological fluxes from it. These are all the type of the different data sets, starting from a coarse resolution, ERA 5, and then we have the downscale version of the ARDO data, which is developed by the URAG research. And then we have also the availability of SERA data. So we will try to use all these data sets and see the variability in the results. Okay, so now the most important part of this case study is about the workflow description. So if you see here, this is the physical base model that I have mentioned, okay, as a starting point to use and compute the hydrological fluxes. Like in our case, we are computing the evapotranspiration, soil moisture, and stream flow in order to forecast the drought events. Once we have the output of the surrogate physical base model, we are developing that surrogate model of this physical base model. As a target variable, we are using the output of the physical base model. Once we have trained our model and minimize the loss function, the second step is to calibrate the parameter. The calibrator of the hydrological model in order to improve it. And in order to calibrate the parameters, we are using some of the additional inputs that we think that which will possibly improve the efficiency of the overall surrogate model as well as the results. After calibrating the parameters, we will put into this the surrogate model, and then we will compare our outputs with the observed data set. And once we have trained the surrogate model, we will use the seasonal forecast data from the ECMWF to forecast the drought events. These are also the possible experiments that we are planning to implement within our studies that we have, using the overall the time series from for 21 years on a daily time scale, and we have divided into the 5 different experiments. Not only on the temporal scale, but we will also use the transfer learning approach, so that once we have trained our model on the temporal scale, we can fix the parameters of the weight, and then there are the 2 possibilities. We will check the trained model into the other catchments, either to keep those initial weights or to freeze it and see how the trained model is behaving in the other catchments as well. Okay, so these are as I have mentioned earlier, that we are using the physical based model, that the W flow as an initial condition to see how the overall this model is behaving. The one thing that we would like to mention here, that this is a semi-calibrated model. They have calibrated this model into the Rhine Basin in Germany, and then by using the pedo transfer function, and then they keep those values and apply the same parameters into the other alpine region. So the main idea just to first see here how the performance of this physical based model, because we are using it as a reference in order to see how its feasibility, either it's behaving the worst results, good results. So according to the initial result, that while comparing the simulated stream flow with the observed discharge station in one of the Adige catchment in South Tyrol, we have seen that it provided us the optimum results. Although it's not like the good results, but at least it's not behaving the worst. So then, after seeing that, okay, the model is behaving, we are developing its surrogate model. So during the surrogate model, we are using, as I have mentioned, the output of the physical, like the soil moisture and actual evapotranspiration, using as a target variable, and then we are developing a surrogate model by keeping all the parameters. The 50 parameters, including the transpiration parameters, snow parameters, soil parameters, evaporation parameters, and also the dynamic data set, in order to keep the physical aspects of the hydrological model. So in the initial 5 experiments, we are trained it by attaching the variables consecutively, like starting from the first, like the 2 parameters, like the dam as well as the vertical hydraulic conductivity, and then we consecutively increase those parameters to see how this deep learning model is behaving. So at the end, the 6th experiment, where we have linked all the parameters. Okay, at the start, there is a rapid increase in the loss. But with the passage of time, as the model is started learning the behavior of the parameters, the loss function is minimized, and then at the end, we have obtained a quite optimum loss function in nearby the 1 in case of evapotranspiration, and approximately near to the 10 millimeter per day in case of soil moisture. So what's now the future perspective is? So as we have now seen that, like, okay, our trained model, by keeping all the physical aspects of the physical based model, and these are the initial experiments that we have run it by using the 4 year of the daily data set that I have mentioned earlier. So now we will check its performance by also varying the temporal extent, as well as by applying the transfer learning approach, also in the other catchments as well. And once we will train, and then the most important step is to calibrate the model to improve the efficiency by using the machine learning application. So maybe the question is how you can improve it. There are already the parameters in it. We have now some understanding about the physical based model. Some of the parameters that they have keep constant. For example, the snow parameters. Similarly, also the soil parameters, which some of these parameters they keep constant. But definitely in all the catchments, these parameters are also varying. So the plan is also we will provide a range while training the model so that according to the meteorological data, the deep learning model will understand this range and provide us like some good results accordingly. The second important step is to integrate this W flow physical base in the Docker container, and then calibrate the parameters as I have mentioned by using the observed data and machine learning. And once we will train our model, we will forecast a drought event using the trained surrogate model and seasonal forecast data from the ACMWF. Yes, so that is the plan and our initial results. Thank you for your attention. And if you have any questions, please feel free to ask.
Thank you very much. We have some 3 minutes for questions. If you allow me, I have a short question at slide number 10. How do you control the error during the learning of the model? How do you control the error during the learning process?
Yeah, so basically we are seeing it, as I have mentioned here, that we are basically reproducing the output of the physical base model. As we have used this one, for example, the evapotranspiration and soil moisture that we get it from the physical base model. And this is basically the target of the development of surrogate model. So the first step is to just to be as closer as to the physical base model, so in order to minimize the loss. So that is the thing here.
Thank you very much. So it's still time for a short question with a short answer. So thank you again.
Thank you so much.
Okay, so the next talk is by Philippe Sabot from JRC. It's about AI for FAPR and how artificial intelligence can help to forecast the seasonal Earth observational signal.
Hello, everyone. I'm Philippe Sabot, and I will be presenting the AI for FAPR. The other colleagues, Martin and Michele, are also from the GRC Food Security Unit, and we are collaborating on this topic with E1, the Disaster Risk Management Unit, where Arthur is from. And finally, we are also collaborating with the University of Leeds, where Chetan is from. Why do we do this? In-house, we have a system, a website called ASAP, early warning system. It's vital for real-time crop condition monitoring when the crops will have some adverse effects. So we can issue a warning. So this system is global and at the regional level. So for each region at global scale, we issue a warning, a biomass warning, or a lack of precipitation during the season, during the crop season. For this purpose, we will be using the fraction of absorbed photosynthetically active radiation, the FAPR, which is also highly correlated to the NDVI. Before we were using the NDVI, but now we are slowly moving to FAPR. And in order to forecast the FAPR, we are also exploring deep learning models, as now everybody does. And we are leveraging on long time series weather data, which are used as covariates. So this is the ASAP early warning system. Some of the graphs that you can see here. Every 10 days we have the data incoming on the platform, and here on the lower left corner you can see the observed NDVI values together with the precipitation and the long-term average. Why do we forecast the remote sensing signal? Because it's a key driver of crop dynamics, and it is usually the only information we have in some countries, like for example in Africa. We don't have any ground truth data, but we have only the remote sensing signal. So here you can see how the for example, these are some crop yield forecasts using FAOStat data in Kyrgyzstan and Morocco. So you can see that FFR shown with red color is usually the most important predictor of crop yield in these countries, so with different weather conditions. So the objective of this work is to develop an operational system for regional level FFR forecasting using a multivariate deep learning model. It's a transformer model. This work is based on the hint casting mode, so the experiments done. Hint casting is basically forecasting into the past, because there we have the data. And then we would like to operationalize this system and run it on our website. This is a future step, next steps. And once it's up and running, we would like to retrain it again when the new data comes in near real-time processing. The study area is so 33 countries, European Union, Ukraine, Morocco, United Kingdom, Algeria, Tunisia, and Turkey. Turkey is not shown in this map, it's an error. And the spatial framework is NUTS-2. The data used, so we have the FFR, the target variable, downloaded from the Mars crop yield forecasting system of the D5 food security unit. And then this is aggregated at NUTS-2 administrative level using the average operator and using the crop mask, the arable land. And also we have the ECMWF ERA 5 weather data like rainfall, radiation, temperature. And the frequency of the data, the FFR and the covariates is 10 days. So every 10 days for each region since 2002 until 2022, we have this data. And this is the tabular data CSV file, around 300,000 rows. So you see here how it looks like in a data frame. And yes, so it's not, we cannot explore like the spatial correlation is basically lost. We don't use the raster, we use the tabular data. Some words on our FFR that we use. This is the MODIS FFR product available for 4 days, but it's aggregated to 10 days. And we are slowly moving to the FFR because MODIS, Terra, and Aqua sensors are reaching the end of their live service. So we will be in the future using the VIRS sensors on board the Suomi and the NOAA satellites. And this is the global data set. This a bit on the forecasting horizon. So we forecast the 6 months of FFR, but you will see later how it propagates for 1 and 6 months. This figure was quite interesting to me. So here you can see the model skill, the forecast skill, how it decreases over time. For the short-term weather forecasts, also for the short-term FFR forecast, this is where maybe the covariates like rain and radiation, temperature can be useful because of their lagged effect. So after 3-4 weeks, we can see the effect. Then for the sub-seasonal forecast, here we would need to use some forecasts of these covariates. And then for the seasonal forecast, in the future, we could use also some of this teleconnections data like sea surface temperature and these patterns like El Niño or La Niña. So this is the problem setup. We need to forecast the 6 months, that is 18 decades, and it's the decade 12 is the crucial time for winter and spring crops in Europe. And then the signal could go like this, or like this, or a good season, or maybe an anomalous season, or like this. No, this is just a joke. A bit fast overview of the forecasting models. This is the target series in blue, shown in blue, what we want to forecast, past covariates unknown into the future. So that's this weather data that we are using, or the future covariates. These are, for example, weather forecasts or holidays or days in the week, so time variable. The problem with these future covariates is usually they are not available, they don't have the same time range as the target series or past covariates. Actually, not as past covariates, but only as target series. This is the selected model, the temporal fusion transformer. It's a model from Google. I will not go into the depth because it's also difficult to understand all the aspects of this model, but it's interesting that it accepts future and past covariates, also accepts the static data, and it's a multi-horizon predictor. So it's a sequence-to-sequence, it has a sequence-to-sequence part. So we basically provide 18 decades to the model and then forecast 18 decades or 6 months into the future. And these are the covariates you can see here in the table. For the future covariates, we use the long-term average of all the covariates and long-term average of the target variable, which is the FAPR. We also use the static data, the region ID, and the time index is the time variable, which is also known into the future. And here you have a plot of how it looks like. The first plot is the FAPR, and then you have the decade 12, which is our decade of interest, when to start the forecasts. And then you have the covariates, and in dashed line you have the long-term average of all the covariates and the target value. This is the workflow. So basically we split the data. The X is the X is the feature data, and Y is the ground truth. In classification, it's more understandable, but here it's like this. So the model is trained based on one season, and then it slides until the end, and we forecast on the test years, which the model didn't see. So we have a single model for all regions because we have a region ID, static variable, and we have one model to rule them all rule, and it's a leave 1 year out cross validation. So we have n minus 3 years using the training the model, then 2 validation years to do the hyperparameter tuning, and we predict on a test year. So it looks like this. And we run this on the BiDS' GPU server. I found this logo very interesting, so I put it here. And these are the results. So the evaluation we do per decade and per region. There is the root mean square error. You can see in the beginning that the forecasts are below 0.04, and then they start to increase. And here you see how spatially the root mean square error, how spatially it's distributed. So this is a third decade, forecasting in third decade. And so it's quite stable across Europe and in North Africa. And this is the GIF, how it decreases, how the root mean square error increases over the horizon, the forecasting horizon. And these are some of the predictions. You see in green the observed and in red the forecasted value. So in these cases it's quite good in Sweden and UK. And here, for example, on the left you have a region in Austria where it's not so good, it's following the long-term average. And then on the right it's quite okay, the season is not so good. There is an anomaly and the model forecasted well. And this is, it was compared to the benchmark, to the long-term average here in the gray. So for the first 3 decades, it was better, but then the long-term average was better than the transformer. And okay, these are the conclusions. For the long-term, as I said, for the long-term forecast, the LTA was more advantaged, so we need to expand it to other countries in operational mode, so then we need to fix the season. And it's also useful for the near real-time remote sensing processing because the last observation of FAPR is extrapolated in near real time, so the model is able to predict it better than using the near real time, long-term average. And this was done Europe and North Africa across different climatic conditions, which we try to mimic using the static ID. Okay, thank you for your attention.
Thank you. We have some time for questions.
How do you think that the model would be improved if you had a higher resolution in terms of spatial resolution data?
In this case, we would need more like a time component. So we are focused. We have a 500-meter data working at NUTS 2 level. So I think for us, it's more interesting to have a longer time series than better spatial data.
Hello. So you said you had, or you use a model to rule them all. Did you use this approach to just save some computing time, or is it actually better to use just one instead of multiple models across the regions?
I think it's better to use one model because this is a deep learning model and we increase the data. So one model has all the data from all the regions. If we use one model per region, then I think the long-term average will be better because it doesn't have much data in one region. You have a time series, but then you don't have the other data from other regions. So it's also like a transfer learning because we train one model and then apply it to all. So I think it's beneficial to have one model. Maybe some other models like tree boost and XGBoost could be useful in this case, as you say. So, yeah.
Thanks.
Actually, I have one. You are using only MODIS data for the moment? Have you tried to ingest more data, such as Sentinel-1, SMOS, and to complete with other sources?
Yeah, we use only MODIS data and this weather data. So because we want to explore the full time series since 2002, if we move to Sentinel-2 and 1, we will need at some point to crop the data. So I think then we would have less data. Since Sentinel-2 is 2016, so I think it will be problematic. And for us, the interest is to work at the regional level. So I think that it's beneficial to explore more the time series component than the spatial Sentinel-1 or Sentinel-2 for now.
Well, I think time is off, so we have to move to the next speaker.
Okay, thank you.
Thank you.
We'll continue with the next presentation on estimation of surface particle matter based on IE and satellite observation.
Yeah, hello everyone. My talk is, as mentioned, is on the estimation of ground level PM10 from satellite data. My name is Johannes Stauffer and I work for Thales Service Numérique, where we developed this method together. Air pollution impacts us in our daily life. It impacts climate through radiative effects. It impacts health through chronic exposure to elevated concentration of air pollutants. It impacts environment through excitation, eutrophication, and it also impacts economic activities. So there is a certain importance to set up monitoring tools to support decision and policy makers. As of now, we have different sources to monitor, or different tools to monitor air pollutants. The most common is the Surface Air Quality Network. This can be considered as the ground truth, but it has limited coverage. In Europe, as you see in the figure, we're a bit lucky. We have a lot of in situ stations, but think about other parts of the world, there are much less stations. The reason is that there's a high deployment and maintenance cost of these service quality networks. On the other hand side, we also have chemistry transport models, so-called CTMs. They give you a gridded output on the atmospheric compositions, and as they're driven also with meteorological data, you also have information on meteorological parameters like temperature, pressure, but their computation is very heavy. And the last source is air pollution monitoring, or is data from space. Satellites can be very valuable. They provide information mostly on vertically integrated contents of pollutants. Think about total column of ozone, for instance. In terms of particular matter, which we are interested in today in this talk, there's a quantity called aerosol optical thickness. It's also known as aerosol optical depth, AOT, which is a key variable in characterizing the aerosol loading in the atmosphere. It's a vertically integrated measure of the extinction effect of aerosols. But for policymakers, this quantity is very difficult to interpret, so they are rather interested in another quantity that is actually the concentration of these fine particles, the particle matter, which is more important for them, but it's easier to get in hands and to grasp them. And this PM is one of the key components of air pollution, particularly in Europe, with a very detrimental short and long-term effects on human health. Traditionally, how to determine PM10 concentration from satellite AOTs? You have statistical regression models. This is the most basic approach. We have a method that's called local scaling factors. So what you do, you use data from climatology or CTMs to derive a ratio between the PM concentration and the AOT, and you apply them to the region of interest, and you get an estimate of the PM2.5 or the PM10, whatever you're interested. The problem is it's a relatively simple approach. You have to recalibrate them on each region. And in the presence of multiple aerosol components, this linear relationship that is inherently assumed in this ratio is probably not valid anymore. And the third part, or the third method, is machine learning. And this is where we are looking into today. So there's a little sketch of how we aim to estimate PM10 from AOT data. So on the left side, you have the aerosol loading from a satellite. Here it's MODIS. And the machine learning will calculate the PM10 from the AOT. More precisely, we will use a surrogate model that calculates the PM10 from the AOT. And it calculates the PM10 at the spatial temporal resolution of the satellite. And the surrogate model is trained entirely by simulations from a chemistry transport model. So this is where you get all the information from PM10, AOT, the meteorological conditions, other physical and chemistry quantities. And the surrogate model is supposed to be very fast and light, and much faster and lighter than the CTM, but with a comparable performance. And what we do not do is to train the surrogate model with in situ data. And the advantage is if you don't train them with in situ data, it should be, in theory, easily transferable to other regions of the world where in situ data are scarce, for instance, in parts of Africa or Asia. So how do we build a surrogate model to derive the PM10 concentration from the AOT? We use CLAMP's global composition forecasts. These are a chemistry transport model, a global chemistry transport model operated by ECMWF since 2014, and it provides us with forecasts and analysis of aerosols, trace gas, and greenhouse gas concentrations, and as well as meteorological parameters. And we use 3 months of CAMPS data in summer 2018 to train and validate the surrogate model. We download the CAMPS data from the atmospheric data store of Copernicus, and it has a horizontal resolution that's about 40 kilometers at 137 vertical hybrid levels. In the table, you see the relevant parameters that are available from CAMPS in near real time and are considered relevant by our surrogate model. You have meteorological parameters, boundary layer height, surface pressure, you have dew point pressure, precipitation, you have wind, which is important, and you have also PM10, you have AOT, and visibility, which is a quantity that reflects humidity, temperature, as well as aerosol loading. And again, there's no in situ data used to build our machine learning model. Our modeling strategy, so we perform a regression per grid point, and we split the data into training data, validation, and test data. So we split the CAMPS data into training, validation, and test data. We train the different machine learning models with different hyperparameters on the training data sets, evaluate them on the validation data set, and determine the optimal model and the optimal hyperparameters. And then, as we have just 3 months of data at this moment, we retrain the best model the best hyperparameters on the concatenation of the training and the validation tests and evaluate them on the test data set. So far, we have tested random forest, XGBoost, and CatBoost. And to evaluate these models, we use the root mean square error. And on the figure, you see the cumulative frequency as a function of the root mean square for the 3 different models. You can see that for 60% of the points, we get an RMSE that is less than 5 microgram per cubic meter, whereas for almost more than 80% of the grid points, we get an RMSE value of less than 10 micrograms per meter. And we also see that the CatBoost performs best among the machine learning models. Just the figure on top, it's just to put the RMSE values into context. And when we speak about the elevated levels of PM10 or pollution events, so it depends on how depends if it's the WHO or the European Union, but it's about between 20 on a day, around 50 microgram per cubic meter. So as we saw that the CatBoost is the model that performs best, we retrained it on a training and validation data set and evaluated it on a test data set. And you see again the root mean square as a function of the cumulative frequency. And we see, for instance, that 80% of our grid points have an RMSE that is less than 7 microgram per cubic meter. But we can say, if we compare it to other to chemistry transport models, we can see that we have a similar performance with our machine learning algorithms as this chemistry transport model. Also very interesting is actually the spatial distribution of the RMSE scores. So you have on the left the data points where the RMSE value is less than 5 micrograms per cubic meter. These data points are mostly located in northwestern Europe, continental Europe. Whereas on the right, you see the data points where you have much higher RMSE scores, so between larger than 5 micrograms per cubic meter. And you see that many of these points are located in Eastern Europe and around the Mediterranean Sea. This behavior is still under investigation, but we know, for instance, what could be a reason for this is that the inventories used in CAMS are less accurate in this region than over Western and Central Europe. So in the next step, we have now trained and determined the optimal machine learning algorithm, so we now can use it to real data. And so real data, we use the MODIS deep blue and target AOT at 550 nanometers as input together with other metrological quantities from CAMS. We put it into our machine learning algorithm, and at the output we have the PM10 mass concentration at MODIS resolution. And we apply this to a wildfire episode in southwestern France on the 9th of July 2022. And you see here some preliminary results from this test case. On the upper panel on the left, you see the daily AOT observed by MODIS. You see elevated values in southwestern western France. And on the right, figure of the upper panel, you see the estimated PM10 concentration from the surrogate model. What's interesting, we capture parts of this PM10 concentrations in western France, but also there's a local pollution event that is seen by our surrogate model over Marseille, which is not seen in the AOT of MODIS. And on the lower panel on the left, you see the in situ data, the PM10 concentration from the French in situ network AES-QA. And you see this pollution event over Marseille is also present in the in situ data. And we also see the PM10 concentration, elevated PM10 concentration over the western part of France are also present in the in situ data. And if you want, you can also add then this PM10 concentration simulated from the surrogate model into a dispersion model to simulate the plume dispersion for the next day. And we see the concentration will move or transported towards north. And a bit stronger, a bit zoom into the comparison between the estimated PM10 and the observed PM10. So we see there's certain underestimated, that the surrogate model tends to underestimate the wildfire PM10 concentration, about 40 to compared to 30 micrograms per cubic meter. And we also see that the local pollution event over Marseille is captured by the surrogate model. So to conclude with the level, that first we tested a method to map the ground level PM10 from satellite products using machine learning. We did not use in situ data to train our surrogate model, which allows us to transfer this model to other regions of the world where the in situ data are scarce, where this network of quality data is not very well developed. The results with the MODIS satellite sensor show encouraging results, but their presence are still there. They're still present, and we need to further improve our model. Particularly, we need a much larger training and validation database where we will use several years of CTM simulations from a regional dedicated chemistry transport model with a resolution of 10 kilometers compared to the 40 kilometers of CAMS. And so far, we also like to improve our machine learning algorithm, taking into account, for instance, temporal correlations between the different atmospheric variables. And we also like to predict multiple species like PM2.5 and PM10 at the same time, or gaseous pollutants. Thank you very much.
Thank you very much. If there are questions.
One question. The comparison is me.
Yeah, sorry. There's a light.
Yeah, it's difficult to see. You compare with in situ data only on the cases of France, or do you have run comparison with in situ over other areas? And it seems to be on France quite a large differences, but maybe can it be due to the spatial resolution, which is very different between your estimation and the in situ? Or?
Well, okay. Yeah. First, so far it's a very small database where we train our machine learning algorithm. So it's just 3 months. We really like to extend it to several years, and we hope that this will improve our results. Particularly thinking like CAMS have only 40 kilometers as resolution, though, so spatial resolution. So our machine learning algorithm inherits this spatial resolution from CAMS. So I think with 10 kilometer resolution, when we use Chimera, should improve the results. The second question regarding the in situ data, so far we only validated or looked at the results during this wildfire episode in summer 2022. There are obvious the biases present, but we would like to test different conditions, different countries, to get a better view of what this algorithm can really do.
Thank you. Time to move to the next speaker. Thank you again.
Welcome.
The next speaker is Theodora Celea from GMV, and she will speak about super resolving waste dumps from space with deep learning and with the test case of Romania Region using Sentinel-2 and Spot6.
Hello everyone, I am Theodora, and today I will share our insights from super resolving waste dumps from space using deep learning. We focus on the Romania region, and we are going to use Sentinel-2 and Spot imagery. We'll start with an introduction of the significance of the waste management problem. We continue with the role of super resolution, and afterwards we discuss the method we used and the results we obtained. We conclude and discuss future directions. Our work started from the problem of waste detection, as there it is an increasing quantity of waste at global level. In Europe in particular, there are regulations to limit this waste quantity, and Romania, as other municipalities, needs to take actions. However, on-site waste detection is challenging and even inaccessible in some regions. Earth observation data can provide a solution for this, and paired with AI, it even offered promising results on waste detection. However, this was obtained on high-resolution data, like Spot. If you want to use high-resolution data, we are going to have a high cost of acquisition and also probably a low temporal frequency. So the solution for us was generating synthetic high-resolution data using super resolution based on deep learning methods. So our goal in this work was to provide support for the actual task of waste detection by super resolving the images. However, we argue that the results you obtain can be generalized to similar data, probably one that include urban periphery or agricultural areas. If we use super resolution, we aim to create a mapping function from a low resolution image to a high resolution image to enhance the visual experience and reduce the pixelation. In this work, we apply super resolution on Earth observation data and in particular on multi-sensor data. We've used Sentinel-2 as our low resolution image and we used the spot image as our high resolution data in training. We aim to upsample the Sentinel-2 by a factor of 4. At the moment, there are 2 super resolution multi-sensor datasets, WorldStrat and MuS2. They are both based on Sentinel-2 and vary across their high-resolution data. However, for our use case, they were not suitable because we needed areas with waste detection, which were not identified by our experts in this dataset. And also, we needed the particularities from the Romania region, and since these are global datasets, they had a poor representation of the particular Romania region. So we had to build our own dataset. Our experts, in collaboration with the National Romanian Environment Agency, have decided on 7 cities from Romania, and then we started to create the dataset. Since it's multi-sensor, it comes with various challenges, like time matching between those 2 sensors, spatial extent between those 2 sensors, and the pixel alignment between the images from the 2 sensors. Afterwards, we apply some specific deep learning pre-processing techniques, and we try to solve the following issues. The first pre-processing technique that we apply is common also in computer vision. It's related to patching in order to have smaller data that fits the hardware requirements. We also split our data between training, validation, and testing, making sure we have the distribution from all the cities and from the waste dumps across all the splits. Next, we analyzed how we can work on the spectral values. First, we applied a normalization technique. However, it's not the standardization or the min-max mostly used in deep learning. We use the linear normalization, already shown to give better results on satellite data because it's less sensitive to outliers. Second, part of our experiments are also going to include histogram matching, as we want to put the values from the 2 imagery, from Spot and Sentinel-2, in the same value range. So what we actually did in this work, we, to our knowledge, provide the first benchmark experiment using 18 different super resolution models. Most of these were created for computer vision data, so we tried to see if these models are also able to perform super resolution on multi-sensor remote sensing data. Our experimental setup started with different channel combinations. First, we tested with single bands in order to see if there are any problematic bands. In addition to this actually fits the initial model scope because most of these models were designed to work with only 1 channel. Afterwards, we also experimented with RGB and in the end with a 4-channel combination to see if these models are able to have a good performance also on multi-channel input. Our experiments also tackle the case of color mapping. Since it's multi-sensor, we are not only having to super resolve the low-resolution image, but you also have to see if the models are actually able to learn color mapping or if techniques like histogram matching can actually help. So we selected a few of the results presented in the paper. If you have a look here, we can clearly see that the near-infrared band is the most problematic one from all four. We can also see that in the case of the blue band, the histogram matching actually helps to increase the performance of the models. However, if we have a look at other bands, like red or green, even though the PSNR score increases, we can see the other one decreases. This can happen because after the histogram matching, the overall brightness of the images increases. However, we miss details regarding structural or textural composition. Then we decide to see if we can obtain good results on the same models using RGB data. This actually gave us the best results, better even from the single band combination. And the idea of histogram matching also can be seen here. The PSNR score increases, however, the other one decreases. In our 4-band combination, we got worse results. This happens probably due to the near-infrared band, which has proven to be problematic in this case. If you have a look at the visualization of the data using the smallest model and the largest one, we can see that when you have the example with histogram matching preprocessing applied, the colors are more natural to the initial high-resolution image. However, do keep in mind that the SSIM score was lower. So what did we do in this work? We highlighted the challenges and our experience in creating a new data set to fit a specific needs, and we experimented with a large palette of single image super resolution models and identified that near infrared is a problematic band in our case. The models can learn a certain color mapping. However, histogram matching can be helpful, in particular for the blue band. We identified a series of top models from different categories, like attention or guns, and we decided for our next step. First, we want to use the synthetic data that we generated today to continue the waste detection process in a case of semantic segmentation. Next, we want to focus on developing techniques to handle bands like the near-infrared, and maybe focus on creating a super-resolution model that is intended for both super-resolving and color mapping in hope to solve the problem of PSNR and SSIM indexes. We also have a poster which is based on current results from semantic segmentation on waste detection, which we invite you all to see in the session in the afternoon. Thank you for your attention.
Thank you. We have time for some questions.
Thank you for the nicest presentation. I was wondering whether your problems with the near-infrared band might stem from a different bandwidth between the two sensors. Did you look into that, or what is your idea of what could be the problem?
Yeah, we think that could be also the case. That is our first intuition into this problem. However, we think the problem can also appear when we downsample the spot image at first, because the spot image at first is at 1.5 resolution, and we also downsample it using GDAL at 2.5, and there also might be some alterations there. But we think all of these models were created for RGB data, and we think a more targeted approach could benefit in this case.
Thank you.
Hi. First, thank you for your presentation. And I have a question regarding the generation of the dataset. I'm wondering how you handle the geometric differences between the two sensors, Sentinel-2 and Spot. How did you do the geometric registration? And also, I'm wondering about the processing level of Sentinel-2. Is it bottom of atmosphere or top of atmosphere? And The third question is the number of images that you use for training the model, because I was see that you use one of the deep learning models that is super resolution dense network, and in their original paper for the training they use more than 50,000 images for the training. However, in your work you used maybe more than 2,000. Do you think that the results that you obtained, it is because of this number of images, and if you increase the number of the images in the data set, would improve the results?
Yeah, so I start with the first question. It was regarding how we did the co-registration. For the co-registration process, we used also a GDAL function. However, we want to mention that in the co-registration process, we use the Sentinel-2 as our reference image because the spot is not going to be present during inference, and we didn't want to alter the Sentinel-2 images in this case. For the second question, we use the Sentinel-2 bottom of atmosphere. This is the images that we collected. We chose to do so because they have a level of preprocessing, and we think the features are more enhanced after the preprocessing of atmosphere. And for the third question, yeah, the size of data sets is still a problem in remote sensing. As you know, the largest one for now, it's Warstrat with around 4,000 samples. We came close, almost 3,000, let's say. However, as in any deep learning model, we do believe that more images can actually help. This is a challenge, especially in super resolution, because we are using spot data, which we had to previously acquire. So I think the direction in this area would be to develop models that are able to handle and provide good results even with less data. Thank you.
Thank you. Thank you again. I think we have to move on to the next presentation, and we have noticed that you have a poster, so we can talk to you late this afternoon.
Continue the next presentation on semantic segmentation for a very high resolution presentation by Knes.
So, hello everyone, and thank you for being here. It is my very first presentation at a conference like this, so I'm very pleased to be here today. So I am Axel Rochelle, a research and development engineer from Magillium, which is a French company specialized in geoinformation and image processing, and currently I am working for the AI4Geo project, and so today I will present you the work performed within this project for creating multi-class semantic segmentation maps given some very high-resolution satellite images. But first, let's give a bit of context. AI4Geo, or as we say in French, AI4Geo, is a French consortium gathering 8 industrial partners and funded by the Public Bank of Investment. It aims at producing digital representation of cities, given some satellite data, and also all the intermediate products, as for example the digital terrain model, land cover maps, or 3D model, and so on. But today we will focus on the creation of the land cover map or semantic segmentation maps. To do so, we decided to rely on supervised deep learning technique, since this method succeeded in having state-of-the-art results over the last few years. And more specifically, our method can be divided into 3 main choices we made. So first, the choice of the data used to train our model, then the choice of the model used for the prediction, and finally, how we post-processed our prediction in order to correct them and make them suitable for the next part of our pipeline. First, let's talk about the data. We use satellite data from the Pléiades satellites, which are satellite images with a resolution of 50 centimeters per pixel. And we also needed to have some associated ground truth. And in order to have the model the more accurate as possible, we asked some annotator to manually label some area of interest for industrial purposes. And so at the end, we had a ground truth with 6 classes of interest as the one you can see here, so the buildings, the road, the railways, the high and low vegetation, and the water. And there is also the background, which is here considered as a 7th class, and which concerns all other pixels. At the time when we did the training, there were in total 14 cities, and for each city, 10 tiles as the one you can see here. Knowing that for each city, we kept 1 tile for the validation and 1 tile for the testing. Then, besides the quality of the annotation, another important factor for training a deep learning model is the quantity of data available. Thus, we decided to complete our custom dataset by an open database available online and named OpenStreetMap. Thanks to it, we succeeded in having a dataset around 100 times bigger than our custom one. However, the quality of the annotation of this database may vary from one area to another. For example, they may have some offset between the reality and the ground truth, and there can even be some neighborhood without any annotation at all. Thus, we decided to only use this database to pre-train our model in order to the model to have some relevant features in the first layers, and then to use our custom dataset to fine-tune it, making its prediction more accurate. Once we had our data, we first created a baseline for comparison purposes. And to create this baseline, we just trained it on our custom dataset. And we performed a grid search on the hyperparameters here in bold, namely the architecture, the loss, and the learning rate. So here is the best set of hyperparameters found with the associated metric. And then we repeated this experiment by first pre-training the model on the OpenStreetMap dataset. And so here are the results for both models. First, visually, we can see that the pre-training enabled to get a closer result to the ground truth, especially for the high vegetation, which was difficult to learn without the pre-training. And also it corrected some confusion between here the railways and the road. Or in a more urban area, we can see that the shapes of the building are better thanks to the pre-training. Now, looking at the metric, it's also enabled to get, in total, an increase of 2% for both the mean intersection over union and the F1 score. And if we look at class by class, we can see that almost all classes benefited from this pre-training. However, when in parallel, we decided to train a building-only model, so a binary semantic segmentation model, we succeeded in having a much higher performance than our multi-class model for the buildings. And also, looking at the class proportion, we can see that our dataset is quite unbalanced, and in fact, the railways, which is by far the rarest class, seem to be very difficult to learn. Thus, being able to focus on some classes seemed to be a good idea, and this gave us the idea to replace our multi-class model by an ensemble of specialized one. This had indeed several advantages. First, since binary semantic segmentation are simpler tasks, better performance are expected. Also, using an ensemble of models enabled to select a different set of hyperparameters for each model, and thus more relevant one. And finally, we found that a simple expert rule enabled to fuse this prediction by only letting the user choose an order of priority for each class, and thus this led more flexibility to our pipeline. So now if we look at the result obtained with the ensemble, we can see that this time we obtained results very close visually to the ground truth, and that the use of an ensemble enabled to correct some confusion between classes obtained with the multi-class one. Also in the urban area of Shanghai, we can see that the shape of the building are still closer to the ground truth. And for the metric, we get a much higher improvement than before. Once more time, class by class, almost all classes benefited from this modification. And it is, in fact, the railway, so the rarest class, which benefited the most from this modification. This may suggest that this method might be suitable to handle class imbalance dataset. So once we had our prediction, we we first converted them into shapefiles of polygon, since this is a necessary step for the next part of our work. And we also decided to use some regularization step to still have results closer to the reality by improving the boundary between classes and also by removing some noisy predictions. This also enables to have more flexibility by letting the user choose which regularization algorithm to use depending on the class. For example, we decided to use the GEO10 algorithm, which is a strong regularization algorithm for the buildings, whereas for the other classes, we decided to use the Douglas-Poker algorithm with more or less strong hyperparameters. So I've presented the methods set up within the AI for Geo project for creating semantic segmentation map. This is based mainly on 3 pillars, which are the combined use of a large data set and a more accurate one, the use of an ensemble of specialized models to have some accurate prediction, and finally, a post-processing step to correct the prediction and make them suitable for the next step of the pipeline. This enables to get satisfactory results while letting the user some flexibility. Right now, we are currently trying to still extend our results using a hierarchy of class in order to be able to handle a much higher number of cases. And also, for future work, it is planned to use more specialized models to improve the performance. For example, I think of the vegetation model we saw in the keynote, which can be an ID. Or we can also use more images with more resolution, for example, the one with of the Pleiades Neo satellites. So this is the end of this presentation. Thank you very much for your attention. If you have any questions, please let me know. And thank you.
Thank you very much. Yes, there are questions.
Louis, Thales Service Numérique. Just one question from your presentation. How do you handle class imbalance in binary segmentation?
In fact, in binary segmentation, we didn't. The model just focused on the class he had to predict. So I know what you mean. For creating the dataset, we first make a preprocessing for each class where we select only the pages where there is the class, plus we add some pages, but a little number, without any class in order the model to see some false examples.
And do you have any special processings you do on the loss function? Or
on the loss function, yes, there are some weights I did regarding the proportion of each class, which are computed at the beginning, before the training.
Okay, so you consider background as a class, isn't it?
No, for the statistics, the background isn't used. Yes. Because we divide by the total number of pixels, so it is considered, yes.
Okay, thank you.
I've got a question. Hello. How do you combine the outputs of these ensemble models?
How do I combine?
Yeah.
To combine, we let the user choose an order of priority. For example, if he wants to focus more on natural area, he can prioritize the vegetation classes, which means that the vegetation prediction will overwrite other less prioritized classes.
Did you used ensembles here, so you used lots of separate models. Did you consider using sort of a shared architecture where the early stages were the same, and then you only you had some sort of divergence later in the model, rather than what might be doing a lot of the same processing several times?
No, this wasn't tested, but it might be an idea for a future plan. But yeah, it can be a good idea, for example, to just to save some computing time. But in fact, in our pipeline, we had the possibility to run all this model in parallel for the inference.
I have quick one.
Yeah.
How the model is robust from one town to another? Do you have to train for different kind of towns, small, big ones, or you can jump from one to another without training?
No, to do that, before the training, when creating the dataset, we ensure that we have a lot of variety of different areas to train the model. But then the purpose is to have a model that is general, as general as possible.
Thank you very much.
Thank you.
So, and please allow me to introduce our chair, Céline Tisson from the CNES, Centre National d'Études Spatiales.
You want me to speak again on that? It's just we started with that, but we were not very numerous in the room. So again, quick announcements. There are some slots for the lightning talk and the bird of feathers. So please connect on the website here if you want to take the remaining slots. And I will conclude the session.
We would like to thank you to all presenters for a very interesting and really useful presentation. We thank you for all the participants. I think, I'm looking to Pierre, that this session was really a session of big data, because all the presentations, they were fulfilling the V of big data: volume, variety, veracity, variability, and also variability and diversity of the users. So I think that this was a very big data session. We thank you again for all participants and again to the speakers. And definitely, Céline, thank you for organizing it. Okay.